Okay, so we had this application of polynomial inequalities that we went over, and I just want to go over it one more time to make sure I didn't totally confuse you on this. So we have this toy rocket shot straight upward from a launch pad 1 foot above the ground, and it has an initial speed of 64 feet per second. And the first thing we want to do is make a model of this, and we can use this model that we already have for projectile motion. So we're just going to set it up with the information we have. S of t equals -1/2 times 32t squared plus 64t plus 1, because 1 is the distance above the ground that we start at, and 64 is our initial velocity. So in part B, we want to find out when the rocket has a height above 50 feet. We will set this formula so that it is greater than 50. We want this function to be greater than 50. So that gives us this inequality, -16t squared plus 64t minus 49 is greater than 0, because we want to get everything on one side and have 0 on the other side. So this does not factor, and so we have to use the quadratic formula to find out the zeros of the equation -16t squared plus 64t minus 49 equals 0. We have to find the zeros of that function. So we would plug that all into the quadratic formula. So t would come out to be about 1.03 and 2.97. So that is where this function equals 0. So the intervals we're going to be looking at are these. We're going to be looking at -infinity to 1.03, that first 0, then 1.03 to 2.97, that second 0, and then 2.97 to infinity. So what we can do is just check values of t in each interval and see if when we put those into the function, we get something greater than 0. So if we put in 0, which is in this interval, into the function, we're going to get -49, and -49 is not greater than 0. And then if we look in this next interval and we try a number in that interval, we could try 2. S of 2 is 15, and 15 is greater than 0. So that would work in that inequality. And then if we try a value in this last interval, try 3, S of 3, if we punch that in, we get -1, and -1 is not greater than or equal to 0. So therefore, the only time when this rocket is above 50 feet is going to be in that middle interval between 1.03 seconds and 2.97 seconds. And so if you were to look at the graph of that object, it goes up, it hits 50 feet, then it keeps going above that, then it comes down. So the rocket is above 50 feet when the time is between 1.03 seconds and 2.97 seconds. Okay, variation, which is section 3.7. As I said, you did this in Algebra 2, so you probably recognize it. Let k be a non-zero constant real number. The statements on the left are equivalent to the equation on the right. We could say y varies directly as x, or y is directly proportional to x. They mean the same thing. If that is true, then y equals kx. If we say that y varies inversely as x, that's the same thing as saying y is inversely proportional to x, and that would mean that y is equal to k over x. Note the value of k is called the constant of variation, or I usually call it the constant of proportionality. So if we want to set up a model using direct variation, write a variation model using k as the constant of variation. The amount of medicine A prescribed for a physician varies directly as the weight of the patient, W. And so we would say A is equal to k times W for direct variation. The frequency F in a vibrating string is inversely proportional to the length L of the string. So we would say F is equal to k over L. The variable y varies directly as the square of x and inversely as the square root of z. So we would say y is equal to kx squared over the square root of z. So joint variation, let k be a non-zero constant real number. The statements on the left are equivalent to the equation on the right. Y varies jointly as w and x. Y is jointly proportional to w and x. That means the same thing. That would be y equals k times w times x. So example 2, write a variation model using k as the constant of variation. Y varies jointly as t, and the cube root of u would look like this. Y equals k times t times the cube root of u. And then B, the gravitational force of attraction between two planets varies jointly as the product of their masses and inversely as the square of the distance between them. So that would look like this. F, the force, is equal to K times the mass of planet 1 times the mass of planet 2 over D squared, which is the distance between them squared. So, example 3, the amount of an allergy medicine that a physician prescribes for a child varies directly as the weight of the child. Clinical research suggests that 13.5 milligrams of the drug should be given for a 30-pound child. So, A, how much should be prescribed for a 50-pound child? Well, the first thing we need to do is figure out what K is. So, if we set this up so that D is equal to KW, where D is the dosage, we can look at that first information they gave us, that 13.5 milligrams are used for a 30-pound child. So we plug in 13.5 for the dosage and then 30 pounds for the child. If we divide, we get that K is equal to 0.45. So now we know what K is. We can look at how much should be prescribed for a 50-pound child. So the dosage would be 0.45 times 50, so K times 50, and that would give us 22.5 milligrams for a 50-pound child. And then a 60-pound child, we would do the same way. 0.45 times 60 would be 27 milligrams. So part C, a nurse wants to double check the dosage on a doctor's order of 18 milligrams. For a child of what weight is this dosage appropriate? So now we know the dosage and we're looking for the weight. So we would have 18 for D, the dosage, equals 0.45 times the weight. And if we divide by 0.45 on both sides, we get that the weight would be 40 pounds. So the loudness of a sound measured in decibels varies inversely as the square of the distance between the listener and the source of the sound. If the loudness of sound is 17.92 decibels at a distance of 10 feet from the stereo speaker, what is level 20 feet from the speaker? I can tell you by experience that it does damage your hearing to be too close to a speaker or to have your earphones up too loud. My hearing is damaged. I use power tools and I did not use ear protection. I have gone to concerts and played with bands and that have brass and that have drums, and I did not use ear protection, and I have constant ringing in my ears and hearing loss. I'm telling you this because it is something that people don't believe, but it really is true. Be careful with your hearing. Use hearing protection. Thank you for listening to this commercial about hearing loss. Anyway, I wanted y'all to know that. I wanted to bring that up because it's important. So anyway, moving on. So we know that the loudness of a sound varies inversely as the square of the distance between the listener and the source of the sound. So loudness is equal to K over D squared, distance squared. And so we can solve for K using the information they gave us. They said that the loudness of a sound is 17.92 decibels at a distance of 10 feet from the speaker. And so we can plug that into the equation and solve for K, and K comes out to be 1,792. So that's our constant. And so the question is, what's the level of sound 20 feet from the speaker? So if we plug that in, L would be 1,792 over 20 squared. And that would be 4.48 decibels. So it goes down a whole lot, more than half what it was when you were 10 feet from the speaker. So it's important to just add a little bit more distance from the speaker. Even in church, it's too loud. So be careful. Solving an application involving joint variation. So this is about hurricanes, and the winds of a hurricane are very damaging. And you can see that picture where a piece of plywood shot through a tree because the wind is that powerful. So we can see that the kinetic energy of an object varies jointly as the weight of the object at sea level and as the square of its velocity. So during a hurricane, 0.5 pound stone traveling 60 miles per hour has 81 joules of kinetic energy. So if we set that up, so we're going to plug 60 in for the velocity, and it's 0.5 pounds. That they told us that's 81 joules of kinetic energy in that object. So now we're going to solve for K, and we get that K is about 0.045. So there's our constant. And now we can use that to see what happens if the wind doubles in speed to 120 miles per hour. So the energy that the object would have then, if we put in 120 for the wind speed, would be about 324 joules.